So the next logical operator that we're going to introduce is probably the most important due to its frequency of use in logic, computer science, as well as mathematics. And that is the logical operator of implication. So let's go ahead and just define implication. So once again, we have a definition, and this is going to be the definition of implication. It is as follows. Seems pretty simple, right? For P and Q propositions, then this bunch of symbols right here, which we can read P implies Q, is the proposition if P, then Q. But this very simple definition right here sort of hides the complexity behind this logical operator right here. In fact, this thing is so important that it comes with a bunch of different names and a bunch of different ways to read it and pronounce it, or different names to call it. So for example, Rosen calls this, in your textbook, calls this a conditional statement. He doesn't call it implication, he calls it an conditional statement. And actually, this bunch of symbols right here, there's a whole bunch of different ways that you can read this. So for example, the way that I've been saying it so far is P implies Q. But there's actually a bunch of different ways that you could say this. So for example, you could say P is sufficient for Q. Or you could say Q follows from P. Or, as I've been saying it with this P implies Q, that's how I'm going to be using it for the rest of this lecture. If you want to see, I think there's like a dozen of different ways that you can actually pronounce this bunch of symbols right here. It's actually contained in your textbook in Rosen page 7, if you would like to see different ways that you could pronounce this bunch of symbols right here. And so what follows in your textbook is the following definition. So what Rosen says is as follows. So Rosen says that P implies Q is false when P is true and Q is false and it's true otherwise. Okay, well, that's a fine definition. And actually, it's useful to construct a truth table with. So for example, using this little definition right here, we can construct a truth table. So let's go ahead and use Rosen's definition right here and construct for ourselves a truth table for this implication right here. Okay, great. So this definition right here says P implies Q is false when P is true and Q is false. Well, P is true and Q is false. That's this second row right here. So that's going to be the only place that it is false, and it's going to be true otherwise. So we have a true up in our first column, in our first row, and our third row, and our fourth row right here. But that might seem a little bit odd to you guys because all of the previous logical operators that we've been looking at have kind of made sense, right? So when we've looked at not, that made sense. All it does is flip the truth value of whatever proposition that you're talking about. And if you were using a logical operator or, it's either or, if either one of them or both is true, then that statement is true. And, well, both of them have to be true for it to be true, and it's false otherwise. An exclusive or was slightly more complicated, and it's going to be true if either one of them are true, but not both. This one right here, it just sort of falls from the sky. And so this is the definition, and this is how it's explained right here. But personally, I find this definition right here a little bit difficult to understand. It's not super clear because it basically just requires you to memorize this particular definition. And so, for example, when you run into particular instances of P and Q, it might not be immediately obvious if P implies Q. So, for example, let's look at the following. So, here's an example. So let's go ahead and let P be the statement or the proposition the sky is always purple. And let's let Q be the proposition everyone has $1 million. So if I were to ask you, if the sky is always purple, then everyone has $1 million. Is that a true statement or is that a false statement? Right? Because we know this particular proposition, that's definitely false. The sky is not always purple. And this proposition here, everyone has $1 million, is also false. So if the sky is always purple, then everyone has $1 million. It's not super immediate from the definition right here. And in fact, you would have to memorize this little thing right here to be able to figure out what the truth value of this compound proposition P implies Q is in this particular instance. And you can if you want to. So for example, we know that this particular statement or proposition right here has a truth value of false. And we know that the truth value of this guy is also false. So this compound proposition right here is actually the same thing as false implies false. So if we go back to Rosen's definition, well, it's false when P is true. Oh, P is not true. And Q is false, and it's true otherwise. So it actually turns out that this thing right here has a truth value of true. If the sky is always purple, then everyone has $1 million is indeed a true statement. And this actually starts to reveal some of the complexity behind this implication right here. And so, instead of just trying to memorize this particular definition and memorize this truth table right here, I think it's going to be a little bit more illustrative if we were to be able to relate this particular logical operation, this implication, back to the ones that we've already seen before. And in particular, to be able to do that, what we're going to have to do is introduce a concept called logical equivalence.